Good morning. I think it's around 8 o'clock now. So today, I would hope I could change slides here. I'm out of battery, I think. Let me just change the battery. So how did it go with the assignments from last week? Maybe while doing this, I can ask or tell one thing. As I said I might do, I have created a peer grade IO kind of example test. I see many of you are on peer grade already, and I saw more of you signing up. Did you get an email requesting to be signed up or something like that? Good. Because I cannot see how it works exactly from your side. I can see some things, but not all things. So what I did was to create an assignment that is basically just to hand in the answers to assignment exercise 3.1. I also uploaded a sample code that you could use for reference using something called knitter. I will probably just show you later today how that works. But it was just to make it easy for you to twist that, to make it your own, and upload that, and then you can see how it works. So hopefully that way, those of you who want to test it, you can also teach me. I mean, at least I will get the experience. You can do it with, say, half an hour of playing around with a few things, presenting what you already did. That's a good recap. That's also constructive. But without doing a lot of extra work. So I hope you will join me on that. And there will be some time for discussing that either today or next week. I will see how I do things. I will ask you later, depending on what the time is. But we'll take it from there. So today is again about regression-based models. We did something last week, which was, you can say, just a general linear model in the matrix settings. Today, we'll do what is called global trend models. And I will either do some examples or I will actually get started on the lecture for next week, because that will help you out for the assignment that will be available a little bit later today. And I think from the feedback from last year, that's probably more constructive. But I'll get back to that when we get there. Still no response. OK, I'll do it the old-fashioned way. So linear regression models. When we do it, actually also as you did in one of the exercises from last week, you took time as being the variable, the x variable that you used, or the independent variable. So was that a smart thing to do? Well, of course, yes. But did you notice one thing in the solution that you probably did different yourself? Anyone noticing something odd? Yeah, but that was not what I thought of. But just that's another odd thing. So the log transformation, you can say, one could argue that that's a good thing or not. But given 8 observations, it's very difficult to say which one is better. It has also different interpretations in the particular case. Because if you do the log transform, you will ensure that there are no negative values. Whereas if you do not do the log transform, you can kind of consider the wind speed in a direction. So it's OK that it becomes negative. It's just the wind turning. So you have different interpretations of it. That was not what I thought of. The problem is, basically what it did was also similar to what we're going to talk about today. So you have functions of time. You have an index here. But what you did previously was to take time from the beginning of time. What we'll do today is to take time relative to now. So every time we get a new sample, we will update our reference time point to be time 0 is now. And why the heck will he want to do that? Well, the naive model, as said, is to just take time in a continuous way. And the alternative, as I just said now, is we'll take time relative to now, as in relative to the newest observation, we'll use time there. So what does that mean? What is the interpretation of the parameters, the phi 0 and phi 1, and phi hat 0 and phi hat 1? How are they different in the two different definitions? Think of that for a short while. Any suggestions? What is the difference in the estimate? Yes?
I think we calculate the parameter regarding the latest information we have up to less error.
No, actually, I mean, when doing predictions, we get the exact same estimates with the exact same uncertainty. So it's a different representation of the same model. If you do a linear model and you say it's years since 2000, or if you do it, it's years since the beginning of time, you get the same prediction. There's a but. The interpretation of the parameters are different. So when you take this definition up here, you have a slope, phi 1. Well, that's obvious. You have a slope down here. Whenever you go one time step further, how much do you increase or decrease with? Those estimates should be the same. But the intercept here, what is that? That is the value that you have when the reference time is 0. So the intercept is you can say you have some point, and let's just say we fit the line. Now, if this here is year 2000, and this here is 2006, then if you have the naive notation, the intercept here might be negative. Even though it's, say, a commodity, that will never be negative. Say the value of houses, stuff like that. So you can say you get some artificial estimates that doesn't really give you any sense. Whereas if you do the other formulation, basically what you do is that you change the scale. So this is time 0, and this will then be time -6. In this definition, that value there will be phi 0 hat. So that means actually, without doing any further calculation, the parameter you estimate is the estimate of the current state. Whereas if you use the naive formulation, you need to do some more manipulations. It also means that if you want to do a prediction, what should it be out here? In year 2007 or 1? How do you? Yes?
Phi hat 0 plus phi hat 1.
Exactly. So and that's what we will be doing repeatedly to make one-step predictions. Now we just have to add two numbers. Whereas if you in the other model, you actually have to kind of keep track of where are you in time. So that's one of the motivations, because often in real-time systems, you keep getting new observations. And that means the further you get, the parameter estimate out there has less and less information about the current state, the intercept. Whereas if you use the second notation, what's called the local trend model, or the trend model, you get everything, always you get an estimate that is relative to where you are. It doesn't matter how long time you've been running the system, your estimate is always the same, is where you are and the rate of change. Next week we'll get to what is called local trend models, where you say, well, I will also forget the past. And that's where this, you can say, formulation makes even more sense. Because if you forget the past but have the past as reference, things start to get odd and complicated. But when you just keep in mind that everything is relative to the most recent observation, things are more intuitive. That's basically what I just said. The important thing is, as said also, it's the same model. It's just a different parameterization. I just shift the reference time point. I guess you've all done linear regression and done the same thing. There's one thing that you may also have considered previously. I drew it last week. When you have a fit like this, and you want to put in, say, confidence intervals or prediction intervals, they have this trumpet shape. So what does that do? It means that if you have a reference point that is far back in time, the estimated parameter down here will actually be very, very, very uncertain. You'll have a growing uncertainty of that point as well. But later on, we'll get to settings where it's not as bad to have it out there. The least uncertainty is around the mean value of the x's, or the mean value in time that you have. The reason why it's not a problem and you get the same is due to the correlation between the slope and the intercept. But that's just a reference thing. Now, yes?
Can you just say again, I mean, you said that the prediction and the, what was it, uncertainty in the predictions was the same.
Yes.
So what was it that was better exactly? Can you repeat that?
Yes, so the representation, the fit is exactly the same. One thing is that using start of time, you have parameters that reflect that, but often what you want to know is something about the current state. So you get parameters that represent the level now and the slope now. You can say the slope is the same, but when we next week get to a local estimate, so that means that you forget the old measurements and have a higher weight, just like the weighted least squares from last week, then you can say it's even more natural to say everything is relative to the most current state, and then I forget the past. So to some extent, this here is setting the scene for next week, where it will be much more relevant to have this construction. Because right now you get the same estimate. So as such, it's a good question, why? But it's to make it relative.
You'll get a different estimate when you do this.
Well, also in the other interpretation, you will also be able to get the same estimate. It's just a matter of linear algebra. Yes?
What if the observation you get now is actually a
Well, that will be invariant. Having an outlier out here, that will be the same for the local model, where you forget the old measurement, but we'll get back to that next week. So that's why you have to tune, well, we'll get back to that, you have to tune your forgetting. So how much memory do you want to have? Now you have an elastic band, you can choose the strength of it. Oh, I should do one more thing. So how do we solve this? When we have a model of the form, of this form here, if you want to write it up on the usual form to kind of fit a linear regression model, well, we will of course have the observations down to yn, starting from y1. And then if we use this notation here, then we'll have a vector of parameters that is theta 0 hat, and theta 1 hat, plus epsilons. So what should I have in here? To have reference, the reference time should be now. So what should I have in this matrix, the so-called design matrix? Can you see that? A column of ones, yes, but and then say a column of time steps. And of course, that is correct, but what should I have down here? Which number? 0, exactly. So everything is relative. Now I should make it so I have the same. So what will be up here? Close. Yeah, I will write it as minus n minus 1, which is also the same as what you said, because then I can have it as n minus 2. Just because I have 0 here, where I start with time 1 over here, so I have n observations, and to go n backwards, I'm at n minus 1. So that's the definition that we will be using. Now, you can look at each of these lines here as this, and you're very close to what we did last week. So in this case, the function fj, what would that be for this setting here? Can you see that? Maybe it's a little bit tricky the way I'm phrasing it, I know. So we know that each row in here corresponds to f transpose of j. So in this case, f of j should be a column vector with 2 elements. The first one is trivial because we have a column of 1s here. And the other element sorry? No, that's only if you want to forecast. But we want to be able to say that this matrix here has rows. Each row is f transpose of j, the right j, so to speak. And j here is the relative time. J is the difference in time from the last observation. So therefore, it's just j. So it's a fairly simple design matrix that we have. So that's the local trend setting. Which we have right there, 1 over j. That's for the linear model. We can, of course, also make other kinds of model. I'll get back to those later on. So the next step is what I actually kind of promoted this idea with is we want to step forward in time. And what we want to do is to make it easy to step forward in time. So when we get the next observation, we want to redo our linear regression model. And that's actually the scene that we're aiming at. And that's where you can see the difference comes in. So if you go for one step further in time, you just add 1 to f here, to the j. So that'll be j plus 1. Now, can we do that in a more intelligent way? At first, it looks like a complicated way, but later on you'll see that it's actually a smarter way. So what we want to define is you take where you were and then you want to multiply by a matrix so that you get to the next value in time. So that's the definition of this concept of trend models. You have to be able to take the current here and you have to be able to multiply by a constant matrix to get to the one-step prediction. You do it twice, you get 2 steps ahead. So that's the structure there. You have to define the transition from fj to fj plus 1. That's one of the crucial things that you can define that. You can do that for many different models. This is one of the simple models. You basically see, well, basically what you do is you take the intercept and then you just add 1 step further in time for the slope. So that it's a fairly easy one, this particular one. So the more general setting is, as said, the model should be linear of this form. We have the requirement that you can step forward in time by some function of multiplying by some matrix L. You have an initial value, f0, which is just a 1, 0, and then you pretty much define the entire sequence. Some trend models that fulfill these requirements, you can say they are the simple ones. Most simple model that you can make is a constant mean value. Basically, what this will do if you run it is that it will just calculate the average of all the previous observations. Second one is the linear trend model. That's the one I always use as an example because, well, just calculating the mean value is maybe too easy. This is the first step where you can actually see something happening. But if you go to a quadratic trend or a polynomial trend, I mean, you just add more columns everywhere and things get more complicated. You can say, why do I have for the quadratic trend j squared over 2 rather than just j squared? The reason is it makes L look nicer. And I guess when you see the general polynomial trend setting, I think you've seen that structure before, right? Where? Yeah, so that's also the motivation for the half there. That's the Taylor expansion that you do. And you can also do harmonics, where you have some period, and the period does not actually have to match your sampling period. It can be any period. Basically, what this sine of 2 pi over p, this is a constant. Likewise for cosine 2 pi over p. So having this here, and you just multiply by the same number on those two, what does that? Do you know what that does? It's a rotation, and basically what it does is just that it changes the angle. So it's just a rotation of coordinate system. If you go back and think of linear algebra, if you were to rotate a coordinate system, that was exactly what you're doing by some angle. So every time you make 1 step forward in time, you rotate your coordinate system a little bit. That is what happens there. So that's just, you can say, a list of potential models. You can do a lot of other things, But you can say, what I like is you can do polynomial trends, in particular when you get to the local setting next week. Often you assume some local polynomial approximation. That sounds like Taylor again. But you can also have kind of a harmonic approximation. So locally, you fix, sorry, I should say one thing. The period P is fixed. It's not estimated. You only estimate the thetas here. So that's an important, because if you were to estimate P, what would be different? Can you see that? It will indeed be nonlinear. So be outside the scope of linear models. So to estimate this, how do we do that? When I want to estimate, I can give it a theta n here, because each time we get a new observation, we can make a new estimate. So theta n hat, what is that? You ought to know that. If I define this matrix here, I'll define this matrix here as X. What should I write here? I know you've all done it. And I know you will be doing it again. X transpose Y, exactly. Anyone in here not remembering it? Now you know what to do between now and next week at least. Because you will be seeing this and you will be needing it repeatedly. So the structure here is the default estimate, the ordinary least squares estimator, as we will use repeatedly. But I will do one thing more. I will redefine this as Fn inverse Hn. So Fn is X transpose X, and Hn is X transpose Y. And a little bit further looking into what this is, if you look at X transpose, you have this matrix here that you transpose. Now I will make it work here. It will be a little bit messy, sorry. So if I transpose that, I have a row of ones. And then I have a row down here where I have 0. And then I have minus n minus 1. Let me just do it like this. And then I multiply by the 1, colon, 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 1, 0, and minus n minus 1. When I multiply these two matrices together, what you'll see is that number is multiplied by that number. So basically, this column is multiplied by this row. And this column is multiplied by that row. Can you see that? So this is the same as remembering the definition of our f from down here. You have this column here is f of minus n minus 1, right? So I have the sum. Now write the same way as over there. J equals 0 to n minus 1. And then I take f of minus j. And then I take f transpose of minus j. Notice that I have transposed the other one because each row here is f transpose already. So I have this here. Similarly, for H, I have X transpose on Y. I can do the same. Looking at it, I only multiply things that have the same time point together. That's the important thing. That you take those that have the same time reference. Those are the numbers that are multiplied together. And that is what makes life easier. So what we have down here is a similar sum. J equals 0 to n minus 1. And then I take f of minus j, y n minus j. So this will work. To make predictions is the next step. Someone down here said, well, you just have to add, you can say, whenever you go one step forward, you just add the slope each time you make one step forward. So the definition of the prediction is fairly easy. And the variance of the prediction error, I don't know if you recognize that expression, but I'll recap one thing from last week. So last week we had the y hat at some, let's call it t plus l, was equal to x t plus l transpose, and the estimate of theta that we had. That was what we did with some predictor from last week, right? And then we saw that the variance of this y hat t plus l was equal to our estimate of sigma hat square, and then a 1 due to the epsilon, and then there comes something from the trumpet shape here, which was x t plus l transpose, and then we have the usual x transpose x inverse, and then we have x t plus l. Just for this time, I will underline that these are matrices. These are the design matrices. This is a vector and a vector again. So that was what we did last week. Well, we can do the same thing here. This here is so if we do it, just recapping what is written up there to have it as reference later, the variance of y hat n plus l given n, if I include or exclude the yn plus l up there, doesn't matter because it's a constant. Equals, we have the same up here, sigma square, 1 plus, and then we should use the corresponding line here. So what that is f of l, and again we should transpose it. And then x transpose x inverse. Well, we just defined f up here as x transpose x. So that will be uppercase f n inverse, and then we can get the f transpose of l. So that also means that if we keep track of the uppercase fn, then predictions are also easy to make. We don't have to redo everything. And prediction intervals are made in the exact same way as last week. There's no, it's just that the, rather than having x's here, we have the corresponding f's. So that's the exact same thing. Nothing is different. Likewise, for the estimator of sigma hat, well, it's the inner product of the residuals divided by the number of degrees of freedom that you have for the residuals, which is n minus p. So that's straightforward. Now, what we want to make is to make an easy algorithm so that when you get the next observation, life is easy. And that's also where this formulation here has its advantages. Because if you just do it in the naive way with the general linear model formulation, then you have to redo everything every time step. Yes?
In your variance of the y hat, in the last FL, is it transposed?
Oh, sorry. Thank you. It should not be transposed. Thank you for that. It was not intentional there, but I will make some small transpose errors, so I'm happy whenever you correct that. So, updating. What do we need to do? When we get the next observation, we need to update Fn and Hn. Can you see how we do that? So we need to make Fn plus 1. And of course, what we want to is to make it relative to Fn. But if you look at Fn plus 1, the only thing you do is that you add an extra element to the sum up here. What is the, you can say, a little bit strange thing is you take the previous one, that contains all the inner products down to here. What you do is that you add an extra column here, and likewise a row there. So what you will get here is f of minus n, f of minus n transpose. The odd thing here is that you added, you can say, it's the old one that you add. The reason is now you got an older observation. You still have all the new observations there for the design matrix. And h n plus 1, you have a similar thing, but it's not quite the same. What you have to do is you have to first take your previous estimate and shift that backwards in time. Well, you do that by multiplying by L inverse. And then you have, so the reason here is the sum of things that are current time and previous time. So if you look at what you have, maybe I should write it out. It becomes a little bit of looking at indices, which is actually something that you're better off doing on your own. When I increase the sum here, what was f0 here, which was multiplied by yn minus 0, well, when I change the time, now that observation is yn minus 1. So you put it backwards one time, so it should be multiplied by f minus 1 instead of f0. Does that make sense? What was the current observation and was it multiplied by f0? When I get the next observation, well, that one has to be the one multiplied by f0. And the previous previous observation has to be multiplied by f minus 1. Does that? Maybe I should have just, I will walk it through a little bit nicer, I think. So the definition here is sum of j equals 0. Now I go for n plus 1, so it will just be n out there of f of minus j, y n plus 1 minus j and now what I want to have is I want to have something that is the previous hn. So I will take the most recent observation here and take that outside the sum. So I'll take and write f of 0 times y n plus 1. That is one element from this. That is for j equal to 0. So now I'll write the rest here. So now I will start from j equals to 1 to n of f of minus j y n plus 1 minus j. That was the easy part. The tricky part is to say, well, we have this still. F of 0 times j n plus 1 plus. But now I want this sum here to look more like this one up here. So I want to shift the indices here. So I take the sum j equals 0 to n minus 1. Well, then I should say that this is f of minus j. And then I should say minus 1. No, minus 1. And then I should multiply with y. And then n plus 1 minus j minus 1. So the plus 1 and minus 1, they cancel out. So it's just j, n minus j. This is quite similar to what we have up there, except that now all the f's here are to be shifted one step backwards in time. But that's why if I pre-multiply by L inverse, I will step one step backwards in time. So this is equal to f0 y n plus 1 plus L inverse. Let me write it so that you have it. J equals to 0, n minus 1, f of minus j, y n minus 1, and that part there is exactly hn. So now we are where we want to be. f0 y n plus 1 plus L inverse of hn. That's where we want it to be. At least where I want it to be. So the h, that's where you step things backwards and update it. So the nice thing here is you have to keep track of a 2x2 matrix that is Fn and a column vector with 2 elements. The next time you get an observation, what you have to do for F is to make a simple 2x2 matrix and add those two. For H, you have to multiply a 2x2 matrix with a vector of 2 elements, and you have to multiply a vector with a scalar here. So the number of operations you do here to update these two are fairly easy. And then to get the estimate, as written here, you just have to invert f and multiply by h. If you were to do the linear regression model from scratch, you would have to recalculate x transpose x. That's a lot more operations to do, because you have to do all these columns with each other. So the formulation here is also to make it computationally easy. And it will also generalize to the weighted least squares next week. So a brief example, similar to what I have down there. We have 6 points. In this case, the definition following what we have up here is to have it like this. So we have a linear regression setting, time relative to the most recent observation. So you have your time index is from 0 up to -5 in this case. You can calculate f fairly easily. You notice the upper left corner here is just a sum of ones. So it actually gives you that you have 6 observations in this case. And you can easily identify some simple recursions for the other elements here. Of course, for h, that has to do with the observations as well, so you cannot make you have to calculate that. And then you have to calculate this down here. So that's all you need to do to get this working. In R, well, there's one thing I did differently last week, but I want to just stressing it. If I just calculated the manual way, X transpose X as F6 and H6 as X transpose Y, then rather than inverting F6 and pre-multiplying on H6, I would rather solve the equation. So what I solve here is I have F6 theta equals to H6. Writing solve in the way up there is to find the theta that solves this directly, rather than first calculating F inverse and then multiplying on H. It's just numerically more stable. So it's not that it gives anything different, but numerically it's better to, you also use solve to invert F6, but you might as well just do the full operation one go, rather than first inverting and then pre-multiplying. I will not tend to give you challenges where the numerics are an issue, but you might as well do it in a proper way from the start. But sometimes I will write it, you can say, the naive way, just to underline this is actually what you ought to do. But numerically, this is better. So that's the estimate I get. Just as a check, I use the linear model. This is also the time that if you are going to do a general linear model, you use the function LM. The generalized linear model is GLM. They have different outputs, different structures, different ways of doing things. So forget about GLM in R. In this course, just use LM. And of course, we get the same coefficients. So we should be happy as such. And that's the line that we got. Looks okay, right? Now, as I said, well, we want to do predictions in this course. And we can formulate the line as such. But what is prediction without an estimate of the variance? First, we need an estimator of sigma square. You would probably not do this by hand, but the value you will probably find the same. And then we can make the variance of the prediction error up here. It's the usual expression that we also have down here. And the one thing to notice is that what is the order of this polynomial in L? It's a second order polynomial underlying the fact of this parabola here. The further you get away from somewhere, the more uncertain it is. Can you tell me for which value of L is the variance the least? Yes?
At the current state?
No? It was a trick question. Yes?
I mean, not really an answer, but for the roots of that polynomial.
No. Not for the roots. Not for the roots of the polynomial. Yes? No? Look at this drawing down here. It's almost identical.
There must be some kind of slightly negative value. Or the square takes over.
Okay, how many of you have been to high school? If you have a second order polynomial where the coefficient in front of the second order term is positive, you have something like this, right? Where do we have the minimum of a function like this? There, right? How do you find that point? You take the derivative and equal to 0. Okay, it's not difficult. So, if you take the derivative of this part in here and solve it equal to 0, well, you have a second order here that makes you multiply on this to get a roughly 0.1, and then you have a little bit more than 0.1, and then you have this one that comes out as a constant, and you divide the two numbers with each other, and you get something close to 3. You had 3 point something, I think it should be. You have 6 observations. You get the least variance when you're in the middle of that. Anyways, that irritates me a lot, this thing. Just as an example, what we would care about is the one-step prediction. So we get a variance that is a little bit higher than the estimate that we got for the sigma square. So that is what should be expected. A little bit or a lot higher, that depends a lot on the structure of your data. And of course, having an estimate of sigma, we can also get an estimate of the prediction interval. Here I use a 90%. Most often I will actually probably use a 95% prediction interval, but I will tend to just change it a little bit, not to make it a default, you always multiply by 2. So I will change a little bit, but I'll also ask you to do different things. So be aware of what I ask for, a 90% or 95%. Those are the usual suspects. So that is the prediction that we get, including our 90% confidence interval. And if you look at it intuitively, it makes sense. Now, the next thing is that you get a new observation. So then we walk through what we have down here. Update F first. Then you update H. And of course, the inverse of L. If you're going to do this algorithm, you invert that once and save that as a variable. There's no need to keep inverting it every time. Because, I mean, many of these systems are also designed to be computational efficient. So nowadays with computers, it's not such a big thing. But if you use with small embedded devices, power is actually also crucial. Because can you make something that survives based on a, say, solar cell or something? That's nice. If you don't have to go there and give it a new battery, if you don't have to hook up power to your device, to your sensor, to whatever, it's brilliant. I mean, think of a device you can just deploy and leave it out there, able to collect and transmit the data that you want. Have a few of those sensors sitting out around. A bit more complicated than this, of course, but for doing CO2 measurements and particle mass measurements out in the streets. If you go to the city of Copenhagen, they have a huge measuring station. What we have is a small, not Arduino, but similar platform with some sensors plugged in. and then a battery and a small solar panel, and they are transmitting data every 4 minutes or so. I cannot do it more frequently because of the power and also because of the standard that we use for transmission. There are some trade-offs between how much information you send and how often you're allowed to send. Updating F7 and H7, we can calculate the new estimate. Oh, I thought I had a slide with that. So if I add this in here, I get something that is almost the same as the previous thing. Now, I think before giving you some information about assignments, we should have a break. So let's resume 5 minutes past.